Now, what's remarkable about this, in some sense, or hopefully you find that it's completely remarkable, and you're sitting there awed that by 9 o'clock in the morning, whoa, my mind is being blown away. That's only 9. Okay? My hope is that you see it's like all we started with here was the definition of derivative. And look how far we got. We took definition of the derivative. We went backwards to calculus freshman year, and we said, oh, we shouldn't take this delta t go to 0 business. We should just let delta t be small. That's perfectly fine. And then we derived all this stuff, all these stepping algorithms. So now we know how to solve differential equations. Okay, so we don't want to just throw on the bus, fundamental theorem of calculus and having the definition of integral. So what can we do with that? If we got this far with definition of derivative, what can we do with definition of an integral? A lot, turns out. So let's do some stuff with it. And that will finish up some of our lecture here. Okay. So let's start off with definition of derivative, which is basically you could say, look, if I write this differential equation and I integrate both sides, right, then if you integrate a derivative, the integrand does that derivative. And so you can basically integrate both sides. And what you end up with is y of n plus 1, y of n, right? So you evaluate at the limits. And I'm going to go from t of n to t of n plus 1. So when I undo this integral and I evaluate t of n plus 1 minus the opposite limit, there, that's the left-hand side, is equal to integral from t of n to t of n plus 1 f t y dt. This is exact. This is just an expression expressing this differential equation in integral form. No approximations. But notice something interesting. Let me take this y of n to the other side. And notice that I can do this very easily on the board. And it might be a little harder for you on your piece of paper. Okay, there you go. And I hate when professors do that, but I'm doing it anyway. It's all in the notes anyway. So notice now what we have again. The future solution is what it is now, plus a little bit of something. What do you mean? How do you know this a little bit? Because I'm integrating over a literal sliver from t of n to t of n plus 1, which is a very small sliver of time. So that means I have something small here. So it's looking a lot like our Euler formulas, except for now it's in integral form. Now here's part of the problem. Can I do this integral? Well, if you go with these standard integral tables, like if you they're on the web now. There's like 800 of them. Surely one of them fits on there. But here's the problem. You don't know what y is, do you? So I can give you an f. You can do this integral, but it's a function of y. This is what you're trying to solve for in the first place. So you don't know what y is. How can you do something when you don't know it? Yeah, you see the catch-22 there? Are you confused yet? No? Okay, all right. Did I just spin anybody's head around? No. Okay. Here is the solution to this quandary. You're going to have to approximate that function f. This is exact up to this point. And then what you're going to say is, well, how about we do the following then? Just like before, I'm not going to let delta t goes to 0. What I'm going to do now is say solution in the future is what it is now plus I'm going to approximate this function f by some polynomial. Okay? I'm going to do a curve fit to that function f. Now, the curve fits are interesting because you can fit, you have data, you fit curves to it. And we like to fit all kinds of curves. If it's doing something like this, we fit a parabola to it. If it's doing something like this, we fit a line. You can make up what you want to fit to this thing. Okay? And if delta t is small, it shouldn't change a whole lot, right, over a small step.